what's up, guys? So let's study some hardware verilog problems. So I googled around and I found this Reddit thread where this guy asked if there's like a leak code but for like hardware, aka verilog, and the top one that people voted, I guess the comments talked about, is like this site, hdlbits, and well, actually there's like these two as well, so maybe like I'll play around with a couple of these. I don't know what this is. Okay, yeah, I don't think this is like verilog. What? Okay, quite simple. So maybe we skip this. That's kind of cool though, that you could. Anyway, yeah, back to this site, HDL bits. There's like, I guess, a very fixed and small problem set, so certainly not the 2000 you get from LeetCode. It starts out very simple, but it does look like later on there's like 12-hour clock stuff, LUTs, and game of life, sort of kind of complex, solving game stuff, and a lot of FSM and larger circuits. So I'll just kind of go through, I'll start with the basics. So I already did the basics. These are just assigned statements. I don't think it's very interesting to watch. And I think these are all pretty easy as well. But I'll kind of just run through and kind of like, so it's kind of like dribbling warm up. And yeah, I'll just kind of run through these and then just try to get through this as much as I can until I'm bored, which is probably like 20 to 30 minutes. The other thing I don't like about this website is that they use Icarus to do, so instead of synopsis, they do Icarus, so you can't like assign tick 0, which is quite a bit annoying, but they do support things like logic. But anyway, I just opened all these in like different tabs, so, and I don't know that they save. Yeah, they do save. These are just AND and NOR and XNOR gates, so they're kind of boring. So I'll kind of just run through these and yeah, let's just do it. So there's a lot of reading here for this vector 1 problem, but I think this is just teaching you how like verilog works. So maybe we can just say, build a combo circuit that splits input half word 16 bits into lower and upper bytes. So actually, pretty simple for this one. So let's submit that, work on the next one. Build a circuit that will reverse the byte ordering. So not the bit ordering, because if it's the bit ordering, I think there's like a streaming operation you can do, but the streaming operation, I believe, is maybe only for synopsis, actually, not Icarus. So whatever. But we basically just want to assign to be, I guess like this. So with Vim, it's a lot easier because you don't have to do any addition. 23 to 16, I think, and then 31 plus 8 is 24. So plus 8 plus 8 plus 8 plus 8 plus 8 plus 8. So this will reverse it. And then let's check to see if the other ones are successful. And this is running. And then let's work on the there's no mismatch. Okay, so I guess success. Vector gates, bitwise versus logical operators. Look at the simulation waveforms. The logical OR of the two vectors and place the inverse of B in the upper half of okay. So I get that. So that's what they want for that one. Bitwise OR of the two vectors. So I guess okay. And then what is this? Where's the simulation? Oh, I mean, I guess they merely mean this. Okay, and it's just no tricky thing here. This is, yeah, okay, so that's right. I really like the waveforms that they put out. It's quite nice. This is quite an educational site. Concatenate them and split them up into vectors. Okay. This is, though, 6 times 5 bits, so it's 30 bits, right? Or what? 30 bits, and then this is 8, this is 32 bits. By 2 1 bits, okay, so like this. I think that's actually all that they're looking for. Oh, so I guess I'm just curious if this works. Yeah, I might try this double curly bracket and then left can I do like I'm wondering if this will compile, but this is the cleanest way to do it, is you have this thing and yeah, so this doesn't do that. Okay, that's fine then. Yeah. I think here they don't want me to use a for loop because this one they want me to use a for loop. So I can just do this is just gonna be two, three, 4, 5, 6, 7, submit. So that's 24 bits. So this will replicate this piece will replicate the most significant bit of in by 24 times because this is 8 bits, so 8 plus 24 is 32 bits. Compare all 25 compare all 25 pairwise 1-bit comparisons in the 25-bit output vector. So I see. This is actually a really cool way to do it. Like, without this diagram, you would instinctively want to do this with shoving this into a 5-bit thing and then do a for always and then double for loop, but this is actually quite a bit cleaner if it's this small. So I can just say like assign logic 240 is gonna be first, second, and then so assign first is just gonna be 5 of A, 5 of B, 5 of C, 5 of D, and 5 of E. And then assign second is gonna be 5 of A, B, C, D, E. I guess I don't need this outer one. Let's check this one. Didn't compile. Okay. Missing a closed bracket here. Okay, and then so this can just be the XNOR of those. So pairwise, you'll do XOR, right? XOR says 1 if it's different and 0 if it's the same. So XNOR is the equals operator. We just flip it. Okay. And that's it for this section. Maybe we can do a few more. What do they want me to do here? Oh, okay. So, they just want me to connect like A to in1 and then B to in2 and then the output. They're both out. I have to connect it by position. So one thing is like by position is like really not a good way to do it. In like no interviewer would ever ask you that, because in actual work, by position is actually really bad. Because unlike software, in hardware, a lot of times you can't just arbitrarily create like definitions and functions, because they actually translate to real blocks and units. Um, and so as a result, a lot of times, a lot of submodules has a very long list of ports. So you wouldn't really connect it by position a lot of times. Um, yeah. So I did not, but I mean, I guess like I could just do like, um, you know, uh, output and then input is this module declaration. So, so there's gonna be Q0, Q1, and Q2. The Q2 is also just this, so just Q0, Q1. Um, so Q0 feeds into this. This is Q1, and then Q1, and then Q. So same thing, Q0, Q1, Q2, Q1. Let's double check that this works. Cool. So Q0, Q1, Q2 will go into this mux, and D will also go into the mux. So then the mux will just select, I see. You can't do an and or. So for example, you could say like and D or, yeah. Or you can do and then do like D and then like and so on and so forth, right? So since I already started this logic, I'll just write it like this, where if it's, I guess, 0, we choose D, and if it's, yeah, let me just do this like that. I don't know why auto indents. All right, whatever. 1, 2, 3. So select this 3, then I'll pick this. Select this 2, I'll pick this. Select this 1, I'll pick this, right? And then that's that one. So I guess this is 1 bit. And then the sum is going to be 15-bit, or sorry, 16 bits. So I'll do okay, and then do the same thing here, except 31 is 16. And the C-in will be the carry out of this. So and yeah, these are fed in like this. C out doesn't matter. I'm gonna assign it to something. The sum though will become sum B, and then also the C out will just be C out B. Doesn't matter. It can hang. So this basically carry out goes into here. So then we kind of, this is like an incrementer basically. And yeah, so this does some of the work, and then actually I don't know why you would do this. you might do this because if you cut this off, then you effectively have a 2-lane 16-bit SIMD add operation. So, but anyway, is gonna be equal to the top part is gonna be sum b, and then the bottom part is gonna be sum of a. This is the same problem. Basically, you have two add 16s, and the A's and B's are the same. The C in is also the same. The C out from A carrying over to add B is the same, and then the sum of B like this is also the same. I guess the only difference is you actually have to implement the 1-bit adder. Okay, you have to implement the 1-bit adder. So recall a full adder is so the LSB of full is just gonna be basically like, whatever the lowest bit is, and then the highest bit, which is what we need to carry out, is gonna be on the MSB. See. So instead of having a critical path of C out feeding into the secondary at 16, which is a bit slower, this just has one more instantiate and that does it all in parallel, and then we use the C out to select the answer from one of these. Okay. Yeah, I guess if there's like 20 of these, you might want to do something like, like that, and then concatenate all your inputs. In this case, there's only 3, so it's actually a bit cleaner to do it the other way, I guess. But anyway, C out B and C out C just does not matter. We don't use it. But the AB feeding into it does matter, so and then so now we have the sum of B, so I should call this B0, and then sum of B1, B0 being the one corresponding with the adder that has 0 as a carry and then 1 as a carry in here. So now we have this, this, and this. We need to pick between this based on this. So maybe a cleaner way is like, no, yeah, let's not inline that. Let's do this. So we can say top half equals if C out A is 1, then we go ahead and pick this, otherwise this. And then so top half is going to be picking between one of these based on this here, and then sum A is just the bottom half. Okay. I see. So if subtract is enabled, it'll do the 2's complement, which inverses B, and then adds 2's complement is inversing the thing that you want to subtract, and then adding a 1. So let's see if this, okay. Okay, so this is done. So I think I only have this one problem left. Yeah. So let's maybe do this one. 16i add A, where A is gonna be this. And the cin is just going to be whether or not this is enabled, and then also the sum is just going to be sum A, and then C out is just going to be C out A. So I need logic for sum A comma sum B, and then also need logic for the carry out of A and carry out of B, which isn't used. Okay. So this is the same, except we do this and we do this. And then this goes here, because regardless, we need to propagate this anyway. And then this is just going to be called sum B instead of sum A. And then the C out is just going to be C out B, doesn't really matter too much. It's just going to be sum B comma sum A. And then let's run this. No mismatches, so yeah, I mean Pretty good. These are somewhat basic, and also they give you the answer in terms of a diagram here. I thought the one where you replicate a bunch of stuff to do pairwise comparisons is like quite cool. Definitely learned something there. So it looks like I did 2, 4, 6, 8, 9, 18 problems here. So let's just call it a day, and then tomorrow I'll probably like just spend more time ripping through all these problem sets and kind of looking forward to these harder ones as well. I guess it's good that this is an Icarus Verilog, even though it's kind of dumb because CoderPad uses Icarus Verilog, because Synopsys requires a license. So it's kind of like using an inferior compiler, and then you're training yourself to basically write kind of crappier code, but the crappier code is also the only thing that can run during the interview process. So this is consistent with that. And yeah, that's all I had.